Hello everyone, today we're going to look at applications of the integral. In particular, we're going to look at work, force due to a liquid, and average value. So we'll start with work. If the force, which we call F, applied to an object is constant, then the work done on the object, which we call W, is given by W equals Fd, where d is the distance of the object, the distance the object has moved. If you've taken a physics course before, you've probably seen this formula come up. What we're going to look at, though, is when the force is not constant. So if it's not constant, then we can consider the force to be a function of x. It can be other functions, but we're going to focus on it being a function of x. So we'll call it f of x. And what we do is we move the object a small distance, so dx. So remember, dx stands for a small change in x. If that's the case, then the change in the force is negligible, and we can say that the force over this small distance is f of x. Then the work is f of x times dx. And then we do it again, and then we do it again, and we do it again, and we do it again. And when we do that, when we add up all these works, and then we let dx, again that small change in x, go to 0, that gives us the integral. So the work, the overall work, is the integral from a to b of f of x dx. So a and b are the distances moved. And again, f of x is the function for the force as a function of distance. If it's not a function of distance, then the equation changes a little bit, but we're going to focus on just force being a function of distance. The most famous example is Hooke's law. Hooke's law states that the force applied to a spring to stretch it a distance of x units is F equals k times x for some constant k, and the k depends on the properties of the spring. So, for example, if it takes 20 units of force to stretch a spring of natural length 8 inches to 10 inches, find the work done in stretching it from 10 inches to 12 inches. So first, we need to use Hooke's law to find k. So F equals k times x. F is the force is 20. The x is 2. So again, x is the distance that we've stretched it. We've gone from 8 inches to 10 inches, so we've stretched it 2 inches. So k is 2, and then x is 2, and we're looking for k. So we solve for k, we get k is 10. We're going to plug that into our work formula. So work equals the integral from 2 to 4. Again, the distance being stretched. So from 8 to 10 is 2. From 8 to 12 is 4. So we're not integrating from 10 to 12. We're integrating from 2 to 4, the distance stretched. And then of the integral of k times x, so 10x dx. The integration on this is really nice. You're always just going to get k over 2x squared. So we have 5x squared from 2 to 4. And we get 60. And then it's whatever the units of work is, which depends on the units of force. We're not going to worry too much about the units, so I'm just going to put units. So let's try another one. Suppose you have a string of natural length 50 centimeters. The force required to stretch it another 20 centimeters is 35 units of force. Find the work done in stretching this spring from 55 centimeters to 65 centimeters. So again, we start with Hooke's law. So the force was 35. The amount stretched was 20, and again, we're looking for k. So I'm just going to simplify 35 over 20 and get 7/4. Make sure that you don't round in here, so keep it as a fraction in your problems. You want to make sure that you're keeping all of the values in there. 7 divided by 4 isn't a bad fraction, but if it was, say, 4/7, you want to make sure you keep that whole 4/7 and don't round it all. So we're going to leave it as 7/4. Again, the work is going to be the integral from 5 to 15. So from 50 to 55 is the 5, and then 65 to 50 is the 15. So again, it's really important that you remember that x is the distance stretched and not the length of the spring. So we're integrating from 5 to 15 of 7/4 x dx. Again, we're just going to take our k divided by 2 and multiply by x squared. So we have 7/8 x squared from 5 to 15. And if you do that out, you should be getting 175 again, whatever the units of the work is. Okay, so it's not always going to be a spring, so we have another example here. Suppose the force on an object is given by F equals x to the 2/3, where x is the distance traveled by the object. Find the work done in moving the object 8 units. So force is a function of distance, right? Again, x is the distance. So to set up the work, we're just going to integrate. And we integrate from 0 to 8 because that's the distance the object has moved. And then we're integrating our f, which is x to the 2/3. If we do that, remember we add 1 to the exponent, so we get x to the 5/3. Dividing by 5/3 is multiplying by 3/5. So we have 3/5 x to the 5/3 from 0 to 8. If we do that out, we should be getting 96/5, which is 19.2, and again, whatever the units of the work is. The next application we're going to look at is force due to a liquid. So the force, again we call it F, on an area A at a depth h and a liquid of density W is given by F equals WHA. So that is the density of the liquid times the depth at which the area is times the area. So if the entire area is at the same depth, think of the area of the bottom of some container filled with liquid, then we can use that formula because the distance is constant, the depth, is constant. However, if we look at an area of the side of the container, so something that's kind of perpendicular, then the depth is changing. Part of that area is at the top, part of that area is at the bottom, and then the rest of it's somewhere in the middle. So we'd have something that looks like this. So again, some of the area is down here at the bottom, some is up here in the middle, some is up here at the top. So the depth is changing. And what we're going to have to do is turn that into an integral. So we take a small slice of the area at depth h. We'll call that thickness of that slice dh. Again, a small change in the depth. The area of this slice is L times dh. So it's a very, very skinny rectangle. So length times width is the area. So L is the length of that slice. And that will give us F equals WHLDH. So again, the W from the density, the H from the depth, and the LDH is that area. And again, what we're going to do is we're going to add all those slices together. We're going to let DH go to 0, and that's going to give us the integral. So we have our formula for the force due to a liquid. So suppose we have a rectangular container filled with water. Water has a density of 62.4 pounds per foot cubed, and we're going to find the force on each of the longer sides of the container. So we're looking at the force on one of these sides here. So what we're going to do is we're going to take a small slice, so I've colored that here in red, and no matter where we take a slice, the length of that slice is always the 3 feet, because that length is always the length of the box, which we said is 3 feet. So L is 3, so that's really nice. The depth of the slice ranges from h equals 0 at the top, so remember it's the depth of it, and h equals 1 at the bottom. So remember, our formula is dh, so h is our variable. So our bounds, a and b, have to be h values, or the depths. So the depth starts at 0 at the top, and then the deepest part it goes is that 1 foot, because that's the height of our rectangular container. Okay, so we're going to be integrating from 0 to 1. So we have F equals, again, W is 62.4, A to B is 0 to 1, L is 3, and then H dH. So I can pull the 3 out, and 62.4 times 3 is that 187.2. Integral of h is 1/2 h squared, so I get 93.6 h squared. We're going to evaluate that from 0 to 1, and that gives us 93.6. Our units are pounds. Remember, this is force, so we have the force unit, which is pounds. What if we wanted the force on the smaller sides of that same container? So now I'm looking at kind of the left and right sides. So the only thing that's going to be different here is L. Before L, the length of our slice was the 3 feet because we were looking at this direction. But now we're looking at this direction. So L is that 1.5. And that's really the only difference here. H is still going from 0 at the top to 1 at the bottom. So again, the only difference is that 3 has now become a 1.5. So again, I pulled it out. Integrate, so 93.6 divided by 2 from that 1/2 h squared, and evaluated from 0 to 1. So we get 46.8 pounds. But what if the length of the slice is changing? So before, again, with those nice rectangles, the slice was always the same. The length of that slice, was always the same. So what if I have something like this? So we have the force, we're looking for the force on the plate shown below, which is submerged in a liquid to a depth of 12 meters, and the density of that liquid is 8,100 newtons per meter cubed. So this 12 over here is telling me that it's the depth of the whole thing is 12. And I have this triangular plate. It has a base of 7. It has an altitude of 9. So the altitude is that perpendicular height from the base. Okay, so this plate, you can think of it as like a metal plate. It's submerged into this liquid, again at a depth of 12. So we have to figure out how to find L. So we're going to take a slice. This slice, again, is at depth H. So the depth is from the top down to the slice. So and that is H, what I have written over here. And then hopefully we can tell that our L is going to change. Right? If I took a height over here, at a depth over here, those are different lengths. So L is going to change. How we figure that out is we use what's called similar triangles. So you might have seen this before if you took a geometry class maybe in high school. And it says that if our triangles are similar, which basically amounts to they have the same angles, then the ratio of the sides of the triangle, and that includes the altitude, are equal. So if I take the ratio of the base to the base, that's equal to the ratio of the height to the height, or side A to side A is equal to the ratio of side B to side B. Okay. So what we're going to do is we're going to look at the fact that we have two triangles here. So I'm going to kind of erase what I just drew in here. And we have two triangles. So we've got the original triangle, and then we also have, use a different color, this triangle here. Whenever you cut a triangle with the, in this case the base being parallel, then you always end up with similar triangles. Okay, this angle here is equal to this angle. This angle here is equal to this angle, and they share that angle, so obviously that angle is the same. So these two triangles are similar. Again, I'll kind of clean this up a little bit. So what we're going to do is we're going to look at the ratio of these sides for this triangle, and we're going to look at the base, because that's something really nice that we have. So 7 and L, so that's going to be 1/2 of our ratio. The other half is the altitude. So the altitude of the big triangle is 9, but what's the altitude of the smaller triangle? It's not H, which I have a lot of people try to tell me that it is. So remember, this whole here, this whole length here is H, but I just want the triangle. So what we do is we have to split that triangle up. So we have to remember that this whole distance here is 12. This distance from the top of the triangle to the bottom is 9, which means this distance must be 3. So we got a 3 here. And if I have H and I'm taking away 3, this height must be H minus 3. So that's going to be the altitude of the smaller triangle, H minus 3. So it's really helpful if you draw these pictures out when you don't have nice rectangles where the L is staying the same. Okay, so I'm setting up my ratio. Again, the base of my smaller triangle over the base of my bigger triangle equals the altitude of my smaller triangle divided by the altitude of my larger triangle. And then I take that equation and I solve it for L. So L is 7/9 times h minus 3. The last thing we have to do before we can plug it into the equation is figure out what h is. What h is bounded by, so the bounds for our integral. So the first slice that we would take is at the very top of our plate, and that is when h is 3. So our integral is going to start at 3. The very bottom of our the very bottom of our plate is the distance or a depth of 12. So our integral is going from 3 to 12. Okay, so you got to make sure that you're not going from 0 to 12 because there's no plate up here during the first 3 meters. Okay, so it starts at 3 because that's where the top, again, of our plate is. So the integral is from 3 to 12. So we can plug that in. So we've got our W, again, it's 8,100 newtons per meter cubed. Our bounds, 3 to 12. L is 7/9 times h minus 3. H is h, dh is dh. So I'm going to bring my 7/9 outside, so that becomes 6,300. And then I distributed my h, so I have h squared minus 3h. And then we integrate. So the integral of h squared is 1/3 h cubed. The integral of 3h is 3/2 h squared. Try to put the squared there. We'll evaluate it from 3 to 12. And we get 2,296,350 newtons. So again, it's force, so the unit is newtons. So now we're going to look at average value. If we wanted to find the average value of a certain number of things, then of course we add them up and divide by how many there are. However, we're going to look at trying to find the average of something that's continuously changing. So what if I wanted to find something like the average temperature over a certain time? One way to do that would be to take the temperature every hour and then find the average of those 24 temperatures. Or I could take the temperature every half hour and find the average of those 48 temperatures. Or I could take it every 15 minutes, or every 5 minutes, or every minute, or every 30 seconds, or every second, or every millisecond, or every, 10,000th of a second. So I could keep doing that, and I could make it more and more precise. The more temperatures I take, the more units I have. But if I want to find the true average over, again, something that's changing continuously, we're going to involve an integral. The integral is fairly straightforward. We take the integral of the function, so the integral from a to b of f of x dx, and then we divide it by the length of the interval. So we multiply by 1 over b minus a. Okay, so remember, an integration is a sum. So this does make sense to find the average. We're summing up everything that we can, just it's an infinite sum, so it's an integral. And then we're dividing by the length of the interval versus the number of things. So it should at least look familiar to be an average. So we're going to do some examples. So the temperature in degrees Celsius over a given day is given roughly by capital T for temperature equals 0.001 lowercase t to the fourth minus 0.280 t squared plus 25, where lowercase t is the number of hours from noon. So t goes from -12 to 12. We want to find the average temperature during the day. So we're going to set it up. It's the integral, it's 1 times 12 minus -12, so 1 over b minus a. The integral from -12 to 12 of our, of our function, dt, where t is our variable. So our fraction becomes 1 over 24, and then if we integrate, we get the following, and we're going to evaluate it from -12 to 12. And if you want, you might want to pause the video and make sure that this is the integral you get when you do it out, and then you might want to find the actual value and then make sure it's the same as what I get. So, we plug in our 12, we plug in our -12, we subtract the 2, and we get 15.7 degrees Celsius. The units are always the units of the original function, which hopefully makes sense. You know, the average temperature should be a temperature. You've got this guy is in temperature. This is in hours. This is in 1/hours. So the hours cancel, and we're left with the temperature. You always want to make sure that your units make sense. Okay. So here they do. Let's try one last one. Find the average value of x squared minus 2 over the interval 4 to 8. So again, we're going to take 1 over 8 minus 4 and then integrate across 4 to 8 of x squared minus 2 dx. The biggest mistake that I see people doing is they're forgetting this guy over here. So don't forget, if you don't divide by anything, if you're just taking the integral, all you're doing is finding the total change in it. So the average isn't the same as the total change. It's the total change divided by the length of the interval. So don't forget about that 1 over b minus a part. Again, the integration here is not too difficult. So we get the following. And then when I do it out, I get 1 over 4 times 424 over 3. I want to simplify it. Again, make sure that you keep the exact answer. Don't round in the middle. We get 106 over 3. Right, that's a repeating decimal. You want to make sure you have all of that in there. So just leave it as 106 over 3. Okay, so we've done work. We've done average value. So try them out. Make sure it makes sense. And let me know if you have any questions. Thanks.